Okay, so before we do, so today we're doing the integral test, which is our first big main convergence test for series. Very related to the improper integral stuff that we've been doing over the last couple days. But before that, I want to do a quick recap of what we've done so far. Okay? So we don't lose our bearings, because it's very easy to lose our bearings. Okay, so what have we done so far? So far, we did, so we have we've seen telescoping series. Which ones are those? Yeah, where all the terms in the middle cancel out, right? So a simple example of that is 1 over n minus 1 over n plus 1, right? So that's an example of a telescoping series where you write out the partial sums, and so you always get a bunch of cancellations in the middle terms, and the only ones left are maybe a couple in the beginning and a couple in the end. Also, sometimes it's written as one fraction. You have to break it up, right, using partial fraction decomposition, right? So sometimes you have to do a little bit of work there. And then we have the second kind of series, geometric series. And these looked like c times r to the n, and it starts at 0, right? So you have a constant times r, which is called the ratio, and then that r is raised to a power. This, we said that it converges if absolute value of r is less than 1. And it converges specifically to c over 1 minus r. And then it diverges if the absolute value of r is greater than or equal to 1. So these two are a few of the ones that we can actually find what the sum is, right? Most of the time, all we'll be able to do is to say whether it converges or diverges, and we won't be able to do much better than that. Okay, so we saw one simple test, and it wasn't a convergence test. It was a divergence test. And what is the divergence test? Do you guys remember? You guys remember what the divergence test said? If you have a series, so let's say you take a series.
Series doesn't go to 0 fast enough.
If the sequence a sub n doesn't go to 0, so not the series itself, right? But the sequence. So if So if the limit as n goes to infinity of a sub n, if that is not equal to 0, then the series diverges, right? So basically what that tells you is that you're adding an infinite number of terms, right? And unless those terms eventually go to 0, there's no chance of the series converging at all, right? And so remember, we talked about this. We said that what's important for convergence is not really what's going on in the beginning. It's the tail end. At the very, very end, are those terms going to 0? How? 2 words. F-E. That is fast enough, right? Yeah. Okay. All right. So that's what we know. So then today what we're going to do is we're going to learn the integral test. So it's strongly connected to the improper integrals that we've seen for the last couple of days. And we already kind of saw the idea once before, but we'll go over it again. And so let's talk about that. So we have the integral test. Okay, so here's the idea. take a series. Let's start off with the harmonic series. So let's say you have the harmonic series. What's the harmonic series? You guys remember? 1 over n. Yep. So you take the harmonic series, and what we're going to do is this. So here, let's take a look at we're going to look at the integral from 1 to infinity of 1 over x dx. And we're going to connect the two ideas. So if I draw a little picture of this, let's see. So let's say I've got right here, rough picture here of f of x is 1 over x. So this is the function 1 over x. Graphically, I can represent the series, the partial sums anyway, of as rectangles of width 1. So my picture is off scale, but that's okay. So what's the area of that first rectangle? 1, right? Because it goes up to y equals to 1. Then the next one has area 1/2, right? And so then you keep doing this. Well, let's do one more. This is 1/3, right? You guys agree? And so then you keep going, and then so you have that this last one is 1 over, let's call this capital N. Okay, so take a look at the, what do you notice about the area of the rectangle? So right here, this is the partial sum, right? This is 1 plus 1/2 plus 1/3 plus 1 over n, right? So that's the partial sum of the series, yes? 1 over n. What do you notice about the area of the rectangles compared to the area underneath the curve? It's always going to be greater, right? So notice that, all right, so let's just write this out. So since the integral from 1 to infinity of 1 over x dx, what is that? That we know already from last time that converges or diverges? That diverges, right? So we did that on Friday. That's you can either evaluate it explicitly or it's the p integral with p equals to 1, right? So that diverges. That diverges, and if you compare the partial sums to the integral of 1 over x dx, what did we just say about the sum and the area under the curve? The partial sums and the area under the curve? The partial sums are greater, right? So this is greater. So basically I have that this one right here, this one diverges, right? I already know that, right? Diverges as n goes to infinity. So then the other one that's greater than that, then what has to happen with that one? Yeah, it has to diverge as well, right? Does that make sense? Because I have a larger one, and so the larger one, if the smaller one diverges, then the larger one also has to diverge, right? Does that make sense? So, okay, so this one diverges. So then the series n equals 1 to infinity of 1 over n also diverges. Does that make sense, at least the idea of it? Yes? Thumbs up? Kind of, sort of? Okay, so now what about an example that converges? So I think what I'm going to do, so this is an example of how we use the comparison of the area underneath the curve, the integral, and the series, writing it as a Riemann sum. And then we'll put it together in what's called the integral test. So let's do an example where it converges. Let's do, for example, so take the following series. So very similar, except, okay, 1 over n squared. Okay, so what function am I going to look at to draw my little picture? One over x squared, yeah. So let me take a look at 1 over x squared. So I have, it looks, at least on the right side, it looks similar, right? Except that it's a little bit steeper. But the general shape is the same, except that this time, though, so let's see, 1, 2, 3. This time, though, I'm going to use left hand, or sorry, I'm going to use, so for the other one we used a left hand approximation, right? This time I'm going to use a right hand approximation. So my rectangles are going to look like this. And let's see. All right, so what's the area of this first one? First rectangle. This is 1/2, right? And then this is 1, or sorry, not 1/2, 1/4, because it's 1 over n squared, right? So this is 1 over 4, 1 over 2 squared, right? This is 1 over 3 squared, or 1/9, and then this is 1/16, so on and so forth, right? So this is, oh shoot, wrong way. I'm doing right hand. Okay, so looks like this, right? So this is n, so this is 1 over n squared. Okay, so far so good? So then what we have is, so we know that, so here this is, notice, is this S sub n? Is this my partial sum of my series? So if I write this out, if I were to write out a few of the terms, what would be the very first term? 1, right? Plus 1/4 plus 1/9 plus, and so on and so forth, right? So what do you notice with my little picture? Yeah, it's not exactly the same, right? So what I drew is I chopped off the first one. Any idea why? Because I need this one. Mine really has this one as well, right? So this isn't super important, but notice that this is the first one, right? 1, or a sub 1. This is a sub 2, a sub 3, right? So notice that I took that one out. Any idea why? Yeah, the improper integral that I'm going to use is I'm going to use the integral of 1 over x squared dx, but I'm going to start it at from 1 to infinity, and I can't start it over here at 0 because there's a vertical asymptote right there. So, but that's not a huge deal. It's just something that, you know, you take note. So here, really, my pink rectangles are really s sub n minus a sub 1. Yes? So that's the first. So what I wrote out in the pink rectangles, that's the partial sum, but I took away the very first term of the series. Yes? Okay. All right. So this, if I compare it to the integral, this one from 1 to the area under the curve, 1 over x squared dx. So what is this compared to that one? Less than or greater than? My s sub n minus a1 is less than this integral, right? You guys agree? Okay. But, so what do I know about this integral? As n goes to infinity, that integral, what? Does it converge or diverge? Yeah. The integral converges, right? So then this one, which is less than that one, is going to also converge, right? So this one over here is going to converge as well, as n goes to infinity. So that means that my series, this series, is going to converge. Okay, so that's the idea. So I think what I won't. So I guess at least the idea doesn't make sense. No? Or should we? Do you guys want the proof? Like, yay, good times proof? Yes?
Yeah, I just don't really understand what you're proving by saying like Sn minus A1 is less than that. What's the Sn minus A1? If A1 is...
Well, that's the partial sum, but taking away the first term, right? So if you forget about the first term, so having the first term or not, it's just a number, right? So that's really not going to affect whether it converges or not. So it's really more of a technical limitation. So let's say you forget about that for a minute and you just look at s sub n. So that is, so the partial sums are always less than the area under the curve. Basically, the area of the rectangles is less than the area underneath that curve, right? So since the area under the curve, that integral, as you go off to infinity, that converges. That's equal to some number, 20 or 10 or 5 or whatever. Then that means that since the rectangles are smaller, then that also has to be equal to some number, right? It also has to converge. Because okay, so imagine the area under the curve, right? So this is some number, right? Can you have, if the area under the curve right here, as you go all the way to infinity, let's say that's equal to 20. Can you have that the area of the rectangles, can that be infinity? No, right? Because it's bounded by 20. It's less than it, right? So it can't be more than 20. So how could it be infinite if if it has to be less than 20 at the same time? Yes.
But isn't what you found like the same as, couldn't you have just said like, well, the sum is infinite because the integral is the same like function?
Well, it's similar, right? It's kind of, this isn't a formal proof or anything. It's more of an intuitive kind of view of what's going on. But the approximation and the function are similar in the sense that they're only off by this area that's off right here, right? So this is how much they're different by. And so if the area under the curve of the function converges, then that means that the rectangles, which is basically the series, right? Then that one also is going to converge. And if the function, the integral of the function diverges, like we had in the other one, then the series, which is graphically the rectangles, that one's also going to diverge. Yes?
But why didn't you do the right-hand side?
Aha, excellent question. Why did we, so it seems arbitrary, right? On one we do the left and then on the other one we do the right, so it's like, well, couldn't we have done the other one and showed that it diverged or the other way around, right? Why is that not the case?
Because one is showing divergence, the other one is showing convergence. So it doesn't matter.
Yeah, because so let's say, for example, let's take a look at this one. So let's say, hypothetically, I were to draw them as left hand. Let's see. Now you can do this, right? But you'll see in a minute why this is not what you want to do. So notice that based on the picture that I drew, what I have is that now my series, my partial sums are now greater than my function, right? Yes? So this one is bigger over here on the left. Now the one on the right converges, right? So I have, so think back to the comparison test that we just did yesterday. So you have the smaller one converges. Does that tell you anything about the bigger one? No, it doesn't tell you anything about the bigger one, right? So it's not that you can't set it up. It's that setting it up this way gives you no information, no info. Kind of like in the comparison test, if you have the inequalities in the opposite direction, that just tells you nothing. That's why. So the same thing for the first one. If we would have drawn the right hand like this, then we would have had that, so like looks kind of like that, right? So now I have that this is smaller, right? So it flips my inequality. So this one, if this one diverges, does that tell me anything about my smaller area? I don't know, right? So that's why you don't do it that way, because it tells you nothing. Yeah?
So that's kind of just up to our discretion.
It's what?
Like we can manipulate that however we really see.
Well, no, in reality, I mean, the picture is really more to intuitively understand what's going on. In the integral test, in reality, you don't actually draw the picture. That's just so that you can see it. So let's write down the integral test. So the integral test is basically summarizing all of this information that we just talked about. It's that. So let's write down the integral test. Integral test. Okay. Integrat test. Oh no. Integral test. All right. Okay. So let f be, my computer's freaking out, positive. Okay, so it has to be positive. It has to be decreasing on the interval from 1 to infinity. and let a sub n be defined by that same function. Okay, so then you have two cases, and they're basically the two that we just showed. If the integral from 1 to infinity of f of x dx, if that converges, then what can you say about the series? Series n equals 1 to infinity of a sub n also converges. Right? Then if what is it? No, the I guess all of that is built in. The picture was just to show what it looks like why the integral tells you whether the series converges or diverges. So because we can write it as depending on how we put the rectangles, we can draw it one way or the other. But basically what it comes down to is that they behave in the same way. So if you're comparing the area of the two, if one converges, then the other one also. If the integral is going to converge, then the sum is also going to converge. Yes? So if the integral diverges, then take a wild guess. Okay, not so wild. That's a bit too wild for me. Okay. Well, then the series diverges. Okay, so let's do some examples. So I feel a little sad because I'm not doing the proof, but you guys can look at the proof. But it's basically the idea is what we just did. It's all right here in the pictures. Yes? I don't think you guys want to do the proofing. Anyhoot. Okay, so we're going to test test for convergence. So we want to test. Let's see, the series n equals 1 to infinity of n squared over n cubed plus 1 for convergence. Okay, so what do you guys think about that? Does that fit into any of the, bless you, does that fit into any of the categories that we've seen so far? Like, is it a geometric series? Is it a telescoping series? Is it a, can we use the divergence test? So if I look at that and I take the limit as n goes to infinity, the sequence n squared over n cubed plus 1, that sequence is going to go to 0, right? Okay, so the divergence test doesn't work. So it might converge, it might diverge. So now if you think of this as a function that you integrate, is this something that looks relatively easy to integrate? Relatively. Kind of, right? Kind of. Like if you think of x squared over x cubed plus 1, you go, oh, I kind of remember that, from some at some point in my life. So then you go, okay, so you have to test all of these things. So the integral test is, it's useful, but the problem is that you have to test all these things. You have to make sure that it's positive. You have to make sure that it's decreasing. And then you have to be able to evaluate the integral. So because of this, It's not always the best, but you know, it's a good place to start. Okay, so I do want to make one comment, and I don't really have a place to put it. Well, I'll make it when we get to that point. So let's do, let's check to make sure that it's positive. So what do you guys think about the sequence n squared over n cubed plus 1? It's always positive for n greater than or equal to 1, right? So this one is obvious, right? The top's positive, bottom's positive, so that's okay. Now, decreasing is not as easy to show. You have to do a little bit more work, right? How many ways do we have to show that sequence is decreasing? 2. What are they?
Take the derivative.
Okay, so you can either take the derivative, right? If the derivative is negative, then you know it's decreasing. Or, what's the other way? Show
Okay, so then it's greater than a sub n.
the other way around in this case, right? A sub n plus 1 is less than a sub n, right? Wait, is that what you said?
That's what I said.
Oh, okay, sorry. I misheard. But, so if you can show that a sub n plus 1 is less than a sub n, then it's decreasing. I would probably guesstimate that finding the derivative is a little easier in this case. So let's do that. So f of x is equal to x squared over x cubed plus 1, right? So what's the derivative of that? What do I get? 2x? Sure. Yeah, 2x times x cubed plus 1. Okay. Minus x squared times 3x squared over x cubed plus 1 squared. All right. So that's equal to, so I have 2x to the 4th minus 3x to the 4th, right? So that's negative x to the 4th. And then I have 2x over x cubed plus 1 squared. Okay, so when is this negative? Or is it ever negative? So the bottom is always positive, right? So this is less than 0 when 2x minus x to the 4th is less than 0, right? You guys agree? Okay. Or when x to the 4th is greater than 2x, just if you move it over to the other side, right? And since we're assuming we're only looking at for values of x greater than or equal to 1, right? So then I can divide both sides by x, so that means that x cubed is greater than 2. So that means that, so the derivative is negative when x is greater than what? Cube root of 2. Okay, now, so this is when it's negative, right? And cube root of 2 is a little bit bigger than 1, right? Yes? You guys agree? Okay, now here's a question for you. Does that satisfy the condition of the theorem that it be positive and decreasing from 1 to infinity? No, right? But it is positive and decreasing from cube root of 2 to infinity. Okay, so now think about it. Okay, So you have this little gap where it's not decreasing, it's increasing from 1 to cube root of 2. Is that going to affect whether it converges or not? No, right? Remember, we've been talking about this for a while. We said what matters is that the tail end converges. So when we say here that so this is important to take note here. When we say that it's positive and decreasing on this interval, what we really mean is that all it has to be is that it has to be eventually positive and decreasing. In other words, there has to be a point where after that point it's always positive and always decreasing. If that holds, then that first initial part, you don't have to really worry about that because that's always going to be finite. And so even though it doesn't necessarily start at 1, as long as there's a point where it's always positive, always decreasing, then you're still good to go. Yes? Okay, so that's an important note for you to know. Okay, so dun, 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 dun. Okay, so we continue. We continue off in our quest. What's our next thing to show? So we showed that it was positive. We showed that it was decreasing. What else do we need to show? What's happening? It's going crazy. Okay, what else do we need to show after that? So the positive and decreasing is just so that we can use the theorem. Now we just have to evaluate the integral and see what we get. Okay, so off we go. You guys remember how to integrate, right? I hope. Okay, so let's see. So let's see. Integrate. All right, so we take the integral from technically from the cube root of 2 to infinity of x squared over x cubed plus 1 dx, right? Okay, so how do we integrate this? We'll do this one relatively quickly because we are experts at integration. What do we use? U-substitution. U is x cubed plus 1. Du is 3x squared. So then what we get is this is equal to, let's write it out as, so we have to also change that to a limit, right? So we have the limit as r goes to infinity, right, of the integral, and then I'm going to change this to an r, right? And then, so this is, u is x cubed plus 1, right? So then I end up with 1/3 du over u. Does that make sense? Yeah? I hope. Okay, and then what's the if I change the limits of integration from x's to u's, what's the bottom limit of integration turn into? If u is x cubed plus 1, when x is the cube root of 2, u is going to equal to 2 plus 1 or 3, right? Okay, so then what I get is this is equal to the limit as r goes to infinity of, what's the antiderivative there? ln of u, right? Evaluated from 3 to r. Does that make sense? Okay, and this is, you can easily see that that's going to, what? Converge or diverge? Okay, maybe we can't see it yet. Let's see. Let's do one more step then. So is the limit as r goes to infinity. Limit as r goes to infinity of 1/3 ln of r minus 1/3 ln of 3. Okay, so as r goes to infinity, where does that go to? We have ln of infinity, which is infinity minus ln of 1/3 ln of 3. So that's just going to infinity, right? So the integral diverges. What does that tell you about the series? Yeah, the series is also going to diverge. So then the series n equals 1 to infinity of n squared over n cubed plus 1 also diverges. So because the integral diverges, then the series also diverges. Questions? Questions? Yeah.
The convergence, can you say that it converges to the same thing?
No, not the same thing, because it's not the same. So that's another good question. Notice that the difference is there's that gap, right? So you can bound it by whatever the value of the integral is. So you can say that it's no more than that, but you can't actually say that they're not the same. Yeah, they're never going to be the same. You can use the integral to estimate what it is, but we'll probably talk about that later. Okay, now what do you guys think about this test? Is it relatively straightforward? Straightforward, yes. Is it convenient? Not very convenient, right? Because you have all these things. You have to check that it's positive. You have to check that it's decreasing. And then you have to be able to integrate. And what if the integral is some ugly integral that is hard to find? What if you have to do partial fractions or trig substitution, all kinds of things, right? So the integral test is useful, but if you take a look at that, if you look at the dominant terms, what are the dominant terms in that series? Which ones are the ones that are taken over? The numerator is n squared, and the denominator is n cubed. So if you look at just those, because we're looking at the tail end when n is going to infinity, n squared over n cubed, that turns into 1 over n, right? So if we're thinking of n being really big, it's going to behave similar to 1 over n, and we already know that 1 over n diverges, right? So then your gut, when you look at that, should tell you, hey, that probably diverges because it behaves similar to 1 over n for n large. Yes? Okay, so the next test that we'll learn will use that sort of, I guess, intuition where you look at it and you go, oh, this is going to behave like this other one that I know converges or diverges. So it's very similar in sense to the comparison test for improper integrals, which makes sense, right? And it's called the same, and there are 2. So we'll do those tomorrow. So let's do another one of these, so you get a little bit more practice. Okay, so let's see. How much time do we have? Like 10 minutes? Okay. We'll see if we have enough time to do a full one, but let's do this is really quick, but the P series. Hey, what's going on? The computer's overheating or something. Okay, P series. So, okay, do you guys recognize that? It looks a lot like the p integral, right? So if you compare it to, okay, so you guys remember. So we had the p integral, right? It looked like this. Hey. Okay, 1 over x to the p dx, right? So this one converges. Oh my god. Okay, when does it converge? We're on reserves. Oh no.
Less than 1.
Converges for p greater than 1, actually, and then it diverges for p less than or equal to 1, right? You guys remember that? Yeah. Okay, and then, okay, so this series, so take a look at that series. So if you use the integral test, I mean, without doing any of the work, you would get the p integral, right? And so what does that tell you about the p series? Exactly the same exact thing, right? So if you use the integral test, you can easily see that the p series is going to converge for p greater than 1, and then it's going to diverge for p less than or equal to 1. Does that make sense? Okay, so this one, the p series, just like the p integral, we're going to use a lot when we use the comparison test. Okay, now the question is, do we have time for another? That's 3. I think we do. Okay. What is it? I know. Look, 8 minutes. It's like, oh my gosh, what happened? Crazy. It's like it's going crazy. It cannot function any longer. It's overheating. It cannot write. It's holding on for dear life. I don't know. All the ones I have are too long. What? What is it? Next time. Okay, well next time we'll do the comparison test. And limit comparison test. Okay. Alright. You guys owe me 5 minutes.
Well, what if you have class after class?